The broadcast is now starting. All attendees are in listen-only mode.
Good morning here in the U.S. Good afternoon in South Africa. This is Mark Anderson. Thanks to the partners for joining us today. I'm really pleased that we have Gabriel Sinai today as our presenter, Dr. Gabriel Sinai, I should say. Gabriel is a colleague of mine that I've known for many years and is from the U.S. Geological Survey at AROS Center, but it's now working, as you can see on the title slide there, at the North Central Climate and Adaptation Center. I won't go through his whole resume. That was shared, I believe, with you as on his bio, but I wanted to mention a few things about why I invited Gabriel to speak. Gabriel is the leader in the country and probably internationally with regards to using remote sensing to estimate water use. And this is a powerful tool to be able to estimate how much water is being used as part of any water budget. And it's especially applicable for Africa, where the cost of data acquisition and compiling that information is so high. This way is a way to acquire that information, because the imagery is free. Gabriel has developed the algorithms to be able to interpret this information and be able to pull this information together. And I wanted to say he also has done work and is specifically knowledgeable about Africa. So without taking any more of his time, I'd like to turn it over to Gabriel and just say I'm so pleased that he's able to finally adjust his schedule and ours to be able to make it happen. So thanks, Gabriel.
All right. Thank you very much for that introduction, Mark. Yes, you're right. I joined USGS to work on Africa as part of the famine early warning system. And what you said about data scarce region, and that's right. The monitoring droughts in Africa was very hard because there is no in situ data. So we looked for satellite data, and ever since 2000, I have been using different satellite sensors for rainfall estimation to now evapotranspiration. So today, I'll be talking about how we generate, estimate, map evapotranspiration for local and regional applications, for drought monitoring purposes, crop water use estimation, and water budget studies. So I've got a lot of a lot of slides. You can stop me anytime and ask questions. I hope this could be an informative and interactive discussion. Moving on. Let's see. So, as I said, I will be showing a lot of work from the US and internationally. I work with a talented group of people from AROS. These are my teammates. So I will have just a one-slide summary in case somebody is really in a hurry to leave. I hope not. And then we'll talk about some global applications of satellite data for drought monitoring. I'll walk you through some background principles, how we use remotely sensed data for evapotranspiration. Specifically, AROS developed a SSEBop that I'm a lead developer, and then some applications on that. And also towards the end, how we're migrating or tinkering towards towards cloud computing. Especially when it comes to Landsat data. Data volume is huge, so we're using some cloud computing resources to estimate evapotranspiration. My summary slide would be this. So evapotranspiration ET is being generated globally at a global scale using a thermal imagery. We use MODIS for global application for now. And so it really uses two sources. One is data coming from a satellite, in this case MODIS, thermal data, but also we need an accompanying important data, which is the weather data sets for potential ET. So the MODIS gives us, a way to get to the actual ET. So I'll talk about how we do that. And with Google Earth Engine, historical Landsat ET has become a possibility now, as I mentioned earlier. With cloud computing, we can go back to early 1980s and we can generate historical ET at a Landsat scale, at a watershed, even in the future global. So the products I'm going to be showing you for drought monitoring purposes, the product has been in use. It's online. I'll show you websites. It can be used. It's reliable as is. But last slide, the last bullet stresses that if you want to use this data for water budget studies where absolute accuracy is important, and we need to do a one-time calibration to remove bias. These estimates are estimates at the end. They are consistent in time and space, but they could have a bias, and this bias could be removed using observed data like Eddy covariance or light symmetry or a water budget-based ET or whatever other alternatives you have. So just to give you a background where we have been developing and working, you might have heard about EROS, Earth Resource Observation and Science Center. This is located in South Dakota, Sioux Falls, where Mark has been actually a director, acting director for quite some time, and we worked together when he was my director there. We continue to work. So this is in the middle of the cornfield, and you can see these are satellite receivers. This is actually a water tower, but these are the different receivers where we receive data for Landsat, MODIS, and AVHR, and others. People mistake, Landsat is a NASA satellite. It's actually a USGS satellite. NASA launches a satellite, but Landsat is managed, operated by USGS at EROS. We are now on the Landsat 8. Landsat 1 was 1972, and now we are working on Landsat 9 and Landsat Next in the next decade. So I call satellite data the great equalizer. What I mean by that is, we have uniformly acquired data with uniform accuracy level all around the world. So people at EROS who manage Landsat and people in Ethiopia, where I'm originally from, would have equal quality data and for environmental monitoring purposes. So this is an example of a drought monitoring tool we use. This is a picture I took in 2002 in Kenya, and that was really the main purpose of using satellite data, was to monitor drought for fuse, so that food aid could arrive in time, maybe just 2-3 months right after harvest. So this is a Landsat pass, and this is a schematic of our Landsat. So how we use that? Well, we use different sources of environmental metrics. We monitor vegetation index, vegetation situation. We monitor the weather or climate, for example, rainfall or temperature. We also monitor hydrologic parameters like soil moisture, evapotranspiration, water levels. But we combine all this with field information for FuseNet, could be grain and the cattle prices, nutrition levels, so we can make an assessment of really whether a food aid is needed or not. And we have the website in here. There are a lot of environmental data derived from satellites. This is an example of a convergence of evidence, how we use satellite data. As you can see, these are anomalies, deviations from the median. Just the colors are, the browners are negative anomalies, and gray is just about normal. Blue is above normal. So when you look at, for example, this is just in 2018, last year, the situation. So if you look at in Botswana and here, the rainfall is a supply. Supply is saying, oh, it's below normal supply. And what you see on the left and right are response of the landscape. So ET is how much water is used by plants, right? So that's also, well, supply is low, but the landscape is also saying, yes, I did not have enough rainfall, so plants did not transpire as much. NDVI is just the health of the vegetation. You might have heard about it, the normalized difference vegetation index, and that's also showing below normal condition. So both the supply and the response of the landscape are converging, and that's just, that would lead to something like this. And every week we get together with USAID, FAO, and NOAA, and NASA, but these products will be delivered to USAID, FAO, and other governments. So this is a weekly bulletin available in our website. So just showing you some global products that's available on the website. This is, for example, I prepared this last month. I was supposed to give this talk last month. So this is for July, for example. July 2019. The anomalous conditions for ET. Again, green is above normal, anything brown is below normal. So as you can see in here, even in the US, there are some browner conditions, and it's corroborated by the drought monitor. And globally, and you look in here in Russia and part of Kazakhstan and stuff, is just showing below normal conditions. And this is the northern hemisphere growing season, July. So the focus would be more, it applies more in the northern hemisphere. And those of you who are, of course, in the southern hemisphere interested in that, and this is, I'm just showing you February conditions, a lot of below normal condition in Australia, but in much of Africa, there is part of northern part of Southern Africa, and in Namibia and Angola, some brown below normal conditions. That's a peak growing season in February in Africa. Some of just giving you an idea of what goes into the model. I'll go a little bit in detail in how we do the modeling, just showing you the data now. This is what we call the potentiality, or in this case, a grass reference ET. We produce this daily at USGS Eros, and we post the data over here. It's a course 100 kilometer, but for a potentiality, that's not too bad. And this is an input to the model. And that would, using this and modest data, we will create something like this. What you've seen is actuality, not potentiality, actuality, which means conditioned by soil moisture conditions. So with a scale of 1500 millimeters for annual total, as you can see, much of the ET evapotranspiration happens in the tropics, which is really pretty much the engine of the world, the global energy and water cycle. There's a lot of energy, of course, solar and being close to the equator, but also a lot of rainfall, and you'd expect a lot of ET. As you move away from the equator, energy available is limited, and so the actuality is actually much lower. But it's hard to interpret this. This is good for water budget studies, but for drought monitoring, we convert that into anomaly, so a deviation from a median value of this period. This is for 2008. This is annual total values, and you can see in here really a big drought and part of the western part of Kazakhstan, and part of Australia, and part of Southern Africa as well. And again, this data is available on the website going back through 2003. This is the MODIS Aquad from an Aqua satellite. I'm showing you another year, 2012, which is a known drought year, especially in the US. So below normal drought conditions, but also, Europe is also experiencing drought. And Brazil, especially Eastern Brazil, experienced a drought as well. That's 2012. So this is more close to the latest situation. So what you see in here from March through August decade 2 means August 20. A month is divided into 3 periods. We call them decade. It's a WMO classification. So what happens this season, this growing season, which is a Northern Hemisphere growing season, March to August, you can see a lot of brown conditions in Russia and Kazakhstan. And also part of Spain, and some drought conditions in Kenya as well, and southern Ethiopia. And so just going back, so I was just wondering, how this corresponds to situations on the ground. So I was wondering, looking for news stories in Russia, and this is what I found. So drought in Russia threatens fishermen depend on Lena River. So this is kind of showing some graphic situations, and which is really the evapotranspiration, regional evapotranspiration is showing below normal. This might be the Lena River they're talking about. So I don't know where the picture was taken. So 2018, so now what happens is drought when it happens back to back, that's where it's mostly dangerous. So as I showed you earlier, 2019, now there's a drought in here, and looking at last year also there was a drought. So when it really happens 2 years, 3 years in a row, that's more dangerous for livelihoods. So now how do we go about monitoring, and where do we post the data I'm sure you're wondering, where we have the data. So we have data decadal, which is 10-day data, monthly and annual ET, and anomaly, which is deviation from the median value. It's global in scale at 1 kilometer since 2003. It's available at this website. You come to early warning and environmental monitoring website with USGS. You can click farm and early warning system. You can get the data. A lot of data is available. It's not only the graphics you find, you can download the data actually, both the ET anomaly and the absolute magnitude. You can choose the year, you can choose the months, and you can get the whole world, and you can subset it for your study area. So for those of you who are interested in the background, how the SSEBop model, SSEBop stands for Simplified Surface Energy Balance Operational, or the Operational Simplified Surface Energy Balance Model. I'm going to just give you a quick background and principle. So when we talk about ET, especially monitoring crops, we use it as synonymous as crop water use. It's just amount of water used by the crops. It's a combination of water transpired by the plants through the plant leaves, which is water absorbed through the roots and is transpired, and also evaporation from the soil surface or even from the surface of the leaves. So it's the combination of the two, we just call it ET. We validate our ET data using field flux tower data, and of course we can use Landsat 8 or any other satellite. So I'm going to show you both a mix of MODIS, 1 kilometer data for a thermal, and Landsat, which is around 100 meters for the thermal. So actual ET is estimated using two broad groups of data sets. One is what we call a potential ET, which is the amount of energy and advective forces and aerodynamic forces. So a sunny day and a windy and a dry day will have a much higher potential ET compared to a cloudy day. So, but that's only potential. That potential could be met when all these conditions, environmental conditions, are favorable. When soil moisture is not limiting, vegetation vigor is in good health, and environmental stress like salinity are not affecting. So if these are not limiting, yeah, we can always say, yeah, the actuality is really driven by just the potential, the energy, and the wind forces. But in reality, what affects drought is really rainfall is not available, soil moisture may not be available, vegetation could be sick or not planted with good density, and a lot of nutrition, soil nutrition is not maybe adequate. So satellite data is going to help us on this, on the limitations. So, as I say, the challenge is ET under potential versus water limiting condition. Under potential is relatively easy. It's just weather data can be used to come up with a potential ET. But the limitations have been accounted for using different techniques since the early 1950s. You might know about the crop coefficient factor, which depends on the type of the crop and the stage of the crop. But also we have to account for soil moisture conditions. So this requires a lot of modeling assumptions. So with the thermal data, we don't need to know what crop is growing. So we think the thermal data combines these two factors, the soil moisture condition and the crop condition together. It's just like sticking a thermometer to a kid's armpit and get a lot of health information. So that's the kind of the powerful information we get from the thermal data. So once we have the thermal data, which is really the temperature, the skin temperature of the Earth, whether it's a canopy temperature or surface temperature, that temperature gradient will account for any water stress, agronomic stress, or environmental stress. And this data and this model is being used for water use and availability assessment in the US, for drought monitoring and early warning applications internationally. Just a couple of more slides about the model. So imagine you have 3 fields next to each other, and the satellite data gives you this information. This is at 300 Kelvin, 10 degrees warmer, 20 degrees warmer than this field. So this is pretty much a well-irrigated field, as you can see. It's a much cooler, and its temperature is very close to, if you look at compared to air temperature. So the surface temperature, the skin, is very close to air temperature, which is about 2 meters above the ground, measured above the ground. So what it says is really there is no temperature difference between the surface and the air, so there is no sensible heat. Heat is not lost through a sensibly transfer. So the only way heat will be lost, energy will be lost through, would be through latent heat or evapotranspiration. So this gives us really an anchor point for getting a maximum evapotranspiration. On the other hand, another field, where vegetation is, density is low, very young, a lot of bare area, there is a lot of sensible heat. So the actually heat transfer through evapotranspiration is very small. Why? There are no plants here. So the moisture for much of the area, the moisture is very low. So in here, the AT would be very, very low, close to zero. Not entirely zero, but just to make a point. So the most important driver is this temperature difference, 20 degrees centigrade, or 20 degree, sorry, this should be Kelvin, 20 degrees centigrade or Kelvin difference between a well-watered and a stressed area. So that temperature gradient is really the driver for our ET model. So schematically, the model works like this. You have a weather data that gives you potentiality. This data is available globally, so you can download it. You don't have to, you can calculate yourself. The input data are also available at different spatial scale. So imagine that you can download this data just readily. Now, this comes from a satellite data, this surface temperature from Landsat, from MODIS, from BHR or VIRS. And you can parameterize this model using like air temperature and other parameters. At the end, the goal is to come up with what we call ET fraction that varies from 0 to 1. So this fraction will correct the potentiality. If this ET fraction is 1, which means it's just that well-irrigated field. So actuality and potentiality will be about the same. If ET fraction is close to 0, which is a dry surface, and you multiply this by the maximum potentiality, you will get actuality, which is close to 0. So this is really what we call a two-parameter model, and it follows a satellite psychrometric approach. For those of you who remember psychrometry, which is really a measure of dry bulb and wet bulb measurements, it's formulated in the similar form, and these are the parameters we estimate. We call it surface psychrometric constant, and this is a wet bulb equivalent that we know how to get that using air temperature. So this is really the driver, kind of the equivalent of the dry bulb from psychrometry. So this is just a wet bulb and dry bulb. Dry bulb is just an ambient temperature, and the wet bulb is the one you wrap with cotton and just you wet this. And in satellite data, where do you find this wet bulb and dry bulb? Well, the wet bulbs are the ones well-irrigated areas. We know how to search them. They will act for us as a wet bulb. And the dry bulb is just any pixel, that's the ambient pixel. So really that difference, once we know how to find this and come up with a psychrometric constant, which you have a way to do that, and then readily you will estimate ET using satellite psychrometry. So just one more slide, an example of how this works. So I'm going to walk you through mountain valley irrigated areas in the southwestern US. This is the Colorado River Basin. So I'm going to take you to part of Arizona. I'm going to show you some data, observed satellite data, and how it compares with the wet bulb, dry bulb I mentioned earlier. So this is the satellite image you get. This is just a thermal data. Just even visually, by looking at the thermal data, you can see that these are center pivot, well-irrigated areas, and their temperature is much lower, cooler, around 280, 290. And the bare areas are this desert, the background desert, the temperature is around 720. So you can see in here actually a range of 40 degrees centigrade or Kelvin difference in nearby. So this temperature gradient is again the driver for the ET model. So that's just how we parameterize the model for the psychrometric constant. I will pass that, but I think this one is more useful. Again, we're in the same transect in here. So you can see going from A to C, we pass through a mountain. This is elevation. And this is where the irrigated areas are located in the valley. That's this section. And we have the mountains again. So now let me show you just this. This is for one day, June 23rd, Landsat data was acquired. This is from Landsat. So what you see in here is at point A, 330 Kelvin. That's how it's measured. Now, every kilometer, we just sample the data. And you can see as you go into the mountain, the temperature drops as you would expect. And now what the most interesting part is this in the valley. That's in here where the irrigated pixels are located. As you can see in here, well, really very hot surface temperature. If you step on it, it will burn you. And then just immediately the moment you hit a center pivot, the temperature drops. And then it goes up and down, up and down. So the coldest is somewhere here, and just one center pivot in here. So really, just this temperature, very special dynamics is a function of evapotranspiration. So in here, there's a maximum evapotranspiration where the temperature is cooler because of evaporative cooling. And here, actual evapotranspiration is close to zero because surface temperature is very high. There is no evaporative cooling. That's really the main principle how we can come up with actuality. So this gives us the ET fraction. We multiply this by a potentiality, and we get actuality. So at the end, this is a potentiality is pretty much a regional variable. It doesn't vary as much from point here to here is about 11 millimeters because it's really the potential. But because of water limitation here, you can see the actuality goes close to the potential and it drops to zero. And here, there is no irrigation, and here, maximum irrigation. And this is just kind of a validation tool using NDVI, where actuality is high. Of course, the NDVI index should be high, as you would expect. All right. And potentiality, as I said, is a regional variable. It doesn't vary that much in local conditions. But if it's at a regional scale, it's a very important variable. This is Upper Colorado in the mountains. This is lower elevation, very hot. These two points would have about a 40% difference in potentiality. So potentiality being a very important variable at the regional scale. So where do we get the data? Well, data comes from, as I said earlier, Landsat, it's 100-meter resolution. It could come from USGS. You can acquire that. MODIS is also available from USGS AROS for download. It's a NASA satellite. Model parameters can come from different data sources. For the world, we use a world claim. These are different potentiality available for download. GridMate is for the US, but GDAS is global. Or you can use a station-based Penman-Montes equation solution as well if you are interested just at a local irrigation district. MODIS data looks like this. It's coverage. This is just an example, an 8-day average. Some surface temperature data. As you'd see, the Sahara and stuff, Middle East is a much higher skin temperature, but in the mountains or the Congo, where evaporative cooling is high, the surface temperature is much lower. This is just another look of the potentialities that we produce using the Penman-Montes solution, and this data is available for download. So I'm going to show you an example of how what it takes to produce and what it looks like using Landsat. These are the Landsat path rows, and this is we're looking at the Colorado River Basin, and it takes about 400 to 500 images depending on availability, clouds and stuff. To cover the whole Colorado River Basin. Now, we can do the same thing with MODIS or with Landsat. So at this scale, we publish this. You can see that irrigated areas and mountain forests, they will have higher ET, higher vegetation. It makes sense. So at this scale, you can use any of them at the basin scale, either Landsat or MODIS. Now, the difference comes in when you are interested to localize the information. As you zoom into an irrigation district, this is based on MODIS, a 1 kilometer spatial resolution. This is based on Landsat, 100-meter resolution. And this is a background base map where center pivots are located. As you can see, if you want to monitor or assess the water use of a farmer, individual center pivots, you would go for Landsat, obviously. You cannot even differentiate that with MODIS. But if you're interested in a basin or large scale average value, the average of this and the average of this are supposed to be comparable, generally, and they will be. So that's really the scale. So at what point do you want to make a decision? At a field scale, you want to go for Landsat. At a basin scale, you can get away with MODIS with comparable accuracy. Again, if you have any questions, please stop me. I have a lot of slides. Model performance, how do we evaluate how the model is good? Well, the first thing is really visually, does the spatial pattern, the temporal pattern make sense? We use Eddy covariance flex tower data, and we can also use basin water budget studies, where we can derive actuality if we know the precipitation and the runoff. This is an example of an application, the Central Valley in Palo Verde in California. We generated 30 years of data. I'm just showing you in here, every 10 years since 1990, 2000, 2010. Green is high ET, red is low ET or close to zero ET. This is in the middle of a desert. As you can see, in 1990, much of the Palo Verde irrigation district, these are towns, is fully irrigated, and here, less irrigation a little bit. You see browning fields. But what's obvious in 2010 are a lot of fields, they don't have any ET. So what happened was there was an agreement with the city of Los Angeles and the farmers in Palo Verde irrigation district. If they don't water, the water will go to the city. So really transferring the water right from the farmers to the city. And the farmers were paid about $200 per acre foot. And sometimes it may take, 3 feet of water, so they could get paid around $600 per acre for not irrigating. So this is what happened. This was a following program, and as you can see, satellite data becomes useful for monitoring even the implementation of this kind of agreements or water use. As I said earlier, we started, hello?
Gabriel, hi, sorry, this is Clara from the Sustainable Water Partnership, one of the organizers. I just wanted to interrupt you there because you wanted to have some questions, and I see that there is a question from Louise, and it's actually very pertinent to the section in the presentation at which you're now. So would you mind if I give Louise the word so she can ask the question and you can answer, take a break from the presentation?
Absolutely.
Thank you. Louise, I'm about to give you the word. Thank you, Louise, you're online.
Thank you very much. My question is, what challenges are you facing when you want to access in situ observations in order to calibrate?
Very good question. The first thing is availability of the data. Eddy covariance is the one we're really looking for. It's the closest thing to being, the truth. So in Africa, for example, you hardly see in situ data being available. And once they are available, depending on the PI, the quality of the data is also very important. There are a lot of gaps, and this Eddy covariance stations require very careful monitoring and data cleaning. So really both availability and quality of the in situ data is a problem. And when we go to also a water budget kind of based analysis, again, you need good quality precipitation data over the basin, a good runoff data over the basin. So, and we can assume, I'll get to that later on, we can assume storage change at annual time scale is kind of close to zero. So, but if the precip and the runoff data are not good quality at the gauge, then we cannot really come up with a basin-wide ET. So really availability and quality of data is a challenge. And sometimes they are available and the quality, and the PIs may not be willing to share the data. So data sharing is also a big problem. Thank you for asking that.
Thank you, Gabriel. Thank you for your answer. I think all of us working in Southern Africa can very much relate with what you just said in terms of availability of data and good quality of data and data sharing opportunities. So I don't see any other questions for now. Louise, does this answer your question? Do you want a follow-up question? Louise? No, she's not there. Okay. Thank you, Gabriel. You can carry on.
Sure. So yeah, once you have, the yearly data, you can do some, animation and stuff, and just a lot of interesting analysis, trend analysis, and that's what we have been doing in different basins as well. So this is just where I was going to get to that, what Louis asked, EC tower data and water balance from the US. We used several Eddy Covariance Flux towers data. And again, at least in the US, there are some good quality data, but there are a lot of areas that are missing. It's usually these are the hardest ones to monitor, the semi-arid areas, and that's where we don't have Flux tower data. But the model has been validated in different, like cropland in here, forest areas, grasslands. So depending on how you parameterize the model, these are probably one of the best performing graphics. It's not always like this, but there was good quality control in data. And when you do that, you parameterize the model well, and you have good inputs of the data, and the model performs well. And this is also AmeriFlux Eddy covariance data on in New Mexico. Again, these are difficult areas, actually, shrublands and juniper and grassland areas. And we just published this about 2 months ago. And these are at a monthly time scale. The daily time scales are not as good. As you can see, there are some years we're missing it in here as well. But overall, the model seems to perform very well different ecosystems. So now I'm just going to show you how this could help us also understand water budget dynamics in a basin. So in the US, we use PRISM. This is a data source from Oregon State, rainfall data set, and we use ET from SSEBop model, and we use runoff data from USGS. This is measured data. And what I'm showing you is really how we think about how ET can help us understand basin water budget dynamics. So as you can see in here, this is the upper Mississippi River Basin. There's high rainfall here and low rainfall in the upper basin. So as you can see, there's an annual time scale, some gradation of rainfall, and you would expect ET also to behave similarly, right? Rainfall is a driver, and ET is a response variable. So I'm going to show you ET, but not how the smoothness and how much spatial detail you get from rainfall versus ET. So this is ET, driven by pretty much the rainfall system. As I said earlier, high rainfall leads more vegetation, more ET, and upper basin, low rainfall, generally low ET, but not directly. As you can see, riparian areas where there is a river flows and there is a lot of vegetation and transpiring at a potential rate, and you will see close to potential rate, you can see high ET. So ET being a function of both not only climate, but also soil moisture and vegetation. So the vegetation pattern will give you a lot more spatial detail in the key hydrologic flux, which is ET. So as annual time scale compared to precipitation, ET gives you a more spatial detail, and what's happening to your rainfall. In terms of closing the water budget, so these are independently measured hydrologic parameters. They are related, of course, physically, but they are measured independently. So this is a precipitation from PRISM, really pretty much driven by gridded station rainfall. And this is ET from a model, from the SSEBop model. And this is runoff from, so ideally, precipitation would be divided into ET and runoff. And this two should add up to precipitation. And we did this year by year. So this helps us, and we conclude that ET was 70% of precip and runoff was about 30% for this basin. So this helps us, see like if our model ET is biased high or low. In this case, at a basin scale at least, we are confident our ET model is reliable. So if we look at it, seasonal variability, and this is again for the whole basin, from January to December, you're looking at several years, average of several years of data. As you can see in here, this is a precipitation pattern. So precipitation peaks in May, June for the upper Mississippi River Basin, and runoff peaks somewhere in May. So now the question is, if you look at precipitation, and let's say in July and March, as you can see that there is more precipitation in July than March. But March, there is more higher runoff than July. Of course, obviously, even if there is more precipitation, that's not ending up as runoff because the ET is maximum in July. So where the vegetation is very active and energy is also available. Potentiality is high and the vegetation density is high. So kind of ET explains and helps us explain, why our runoff behaves the way it is. So just a sample application in Africa as well. This is the Blue Nile Basin, and I'm just some focus. So this is the rainfall, and this is ET we derived. So I'm going to show you as an example, how the rainfall variability peaks in July and August, and ET actually peaks in September, where the clouds are over and the vegetation is still active. So just looking at the whole Nile Basin, some of you might be familiar with the Nile Basin, where much of the supply comes from the equatorial and the Ethiopian highlands. And this is, I think I have another slide in here. This is in southern Sudan, the third wetlands in here, and this is Lake Victoria. So this is a highly vegetated area in here. So now what happens? This is ET, and what happened to the rainfall? And as you can see in here, this is what we call a sink. There's a lot of evapotranspiration, a lot of loss in the set. Of course, ecological is very important. I'm not saying it's a useless thing, but there's much of the rainfall generated in here ends up being lost. So the evapotranspiration process at the wetland in here. So generally what we call the source of the river are in here, the equatorial highlands in here, in Uganda and Rwanda, and the Ethiopian highlands, a lot of rainfall. But there's a lot of sink in here, would be the wetland in here, and also a lot of the irrigation water used in the Nile Delta. So the supplies and the sinks. So at the end, these two are supposed to balance to zero. So just a few more slides about cloud computing. There's a lot of data, as I said earlier. So the one phrase I like about cloud computing is this: bring our code to the data instead of data to the code. So in the desktop computing, we have been spending a lot of time downloading the data, Landsat, MODIS, and just takes a lot of time to download. Now, instead of that, the data is already in the cloud. So what we do is just we take our code. So we program right there in the cloud. So there is no downloading of data. The only thing we download is the final result. Because of that capability, we were able to create a first ever Landsat-based annual ET for the US. It takes about 16,000 plus images to create an annual ET. It took us less than a week to do that. Imagine this 10 years ago to do it in cloud computing, desktop computing, which is impossible to begin with. So now we're trying to do this more historical analysis. And once you have the ET data, you can apply a crop mask like this, and you can zoom in and see, where water is being used, whether it's riparian areas or irrigated fields showing higher ET. Then, of course, you can have a lot of tools in Google Earth. You can click on a pixel. You can get information like this. What's the potentiality rate? What's the actuality? You can click around different places. So this is cloud computing with Google Earth Engine is changing a lot of the way we're doing. It's helping us reparameterize the model. When you see something that doesn't make sense, it's not going to take us a month anymore. We can just change a code. Within a few minutes, you'll get a new assessment, a new result. So it really improves our modeling as well. There are 3 panels, where you write your code in here. You can display the results in here, and these are your folders. So those of you who have not jumped and I recommend you to go to the Google Earth Engine code editor, and they have a lot of tutorials. You can pick it up very easily. A graduate student will be an expert within a week. I can create trouble, I can read files, I can interact with my teammates, and it doesn't take much to come to speed. I have a lot of resources. Our data is on the cloud as well, and you can go, this is the climate engine from DRI. They hosted our data. This is the MODIS data. You can click and see time series charts as well. It's available. So it's climateengine.org. Our data, not only MODIS ET, but Landsat and NDVI and weather datasets, global weather datasets are available. So this is a free resource for you as well, especially if you want to test a hypothesis oh, I wonder, you know, what the NDVI said in here, this pixel last year, oh, compared to the drought year. So that data is just a matter of a click, and you get time series charts like this. We are working on OpenET as a multi-agency collaborative ET project. It's by NASA, USGS, USDA, and others in collaboration with a non-profit organization. So anyways, this is my final remark. Global coverage of ET maps from thermal-based ET is becoming more common. Historical Landsat ET can be generated now with cloud computing. Don't forget the validation calibration of ET data. You can use it for drought monitoring as is, but if you want to use it for water budget studies, make sure you calibrate that using any in-situ data. OpenET is a promising, I would say, multi-agency organization that's trying to make ET data freely available. Not only the data, but the models are open source. For example, SSEBop is open source now. It's on the website. Anybody can download it. But all other models, now there are 6 models working together to make ET data freely available in the US to begin with, but to make it global. That's all I have for now. So I will be very happy to take a lot of questions. I know I talk fast, but I'll be very happy to go to any slide or any section. Thank you.
Thank you very much, Gabriel. I'm fascinated that, coming from Transboundary natural resource management and ecosystem management, this for me speaks very much to the kind of information that we need to really understand how an ecosystem works or doesn't, and what are the peak points, and where we should start to get really concerned about land uses for water security. So I really found it fascinating, and I will go and see the websites and pass them on to other colleagues in the field. There is a question that has already been pushed through the system from Gosbert. So Gosbert, I'm going to give you the ability to speak. I'm going to unmute you so that you can ask the question yourself and engage in a conversation with Gabriel on your point.
Sure.
Here we go. Gosbert, the floor is yours. Gosbert? Hello? Gosbert? Can you talk, or are you only on audio? Let me ask him a question. Yeah, Marina, you will be able to get a copy of the presentation. It will be made available to the people who attended while we wait for Gosbert. Okay, let me just ask Gosbert's question then. I think it's going to be easier. Some people are only on audio, and I have no ways of knowing that. So you ask if there is a possibility to assess the future drought conditions using available resources and models. So yeah, based on on your presentation, what would be useful in assessing drought conditions in our region, I suppose, Gabriel?
Oh, I might have missed, but can I repeat? I think saying what models would be useful for assessing drought conditions in which region?
Yeah, in the Southern Africa region. I'm assuming Gosbert would be from Southern Africa.
Oh, okay.
So yeah, please, that would be the question. Thank you.
Okay, so I think if he's not familiar with, they're not familiar with the FuseNet, that's the first stop. There's a lot of products there. The convergence of evidence is a very powerful concept. So they need to look at precipitation, and their satellite chirps is a good data set, and there are the rainfall anomalies that are derived from chirps, not as absolute magnitude or as a standardized precipitation index, SCPI, and soil moisture also derived from that. So using a water balance model. So there are rainfall-based products from the FuseNet side. And of course, the evapotranspiration at 1 kilometer, we call that the ET anomaly, that's available. And NDVI from MODIS, I believe it's 250 meter, very high resolution, even the 1 kilometer for regional drought monitoring and even local. So So I would encourage them to look for rainfall-based products, vegetation-based products, and evapotranspiration-based products. These are all available, and they go back in history, 2000, even earlier.
Okay, thank you very much. Yeah, I'm also taking notes because some of this information is also going to be useful for our teams and our research teams under the collaboration project. I see some of them are still online. Right, are there any other questions that the audience wants to ask Gabriel? Yeah, sorry, Gosbert confirmed that he has a problem with the microphone. Gabriel, have you? Yes, Mark?
Real quick, I was just going to mention if there's a gap while somebody's formulating their question. One thing I forgot to mention in the introduction is there's a pretty good video that features Gabriel on the internet. So if you just Google water use and Gabriel's name, that video will come up, and so you can get a chance to actually see what he looks like. This is doesn't have the video, but also he does a nice job of working with Molly Mop and introducing the capabilities of monitoring water use. So just I didn't see that URL in your presentation here, Gabriel, but that's a good quick introduction to. But you know, again, one of the things I wanted to mention is one of the things we're doing here is not necessarily, you know, preparing somebody to just actually do these analysis, but also expanding your network of contacts for the folks over there, the partners. So, you know, they know who to call. And sorry if we might get, you might get a lot of calls or follow-up information about it, but the idea is expanding the network of contacts, you know, in some of these technical matters that you wouldn't otherwise be able to do without spending a lot of time in the literature and kind of stumbling around yourself. So anyway, thanks again, Gabriel, for your presentation.
Yeah,
absolutely. No, absolutely. I will be happy.
Mark, I take your point. The thing is, I really haven't followed all of the presentation from USGS. There's not one of them that I have not found relevant. And this one specifically, because we're looking at a transboundary aquifer in our program, which is the Ramoto aquifer, it's very interesting because it really can give you the kind of basin idea, and it's not really just about water and how do you monitor exactly the flow of water on the ground. It's more like having a bigger picture. So Gabriel, that's why I find yours particularly fascinating, and because it seems like there is a lot of information that is already available, and it's really just a matter of understanding how to grasp it together, like you mentioned in your response to Gosbert, and then try to understand better what happens in the basin. So it's not about developing a different tool or a different methodology, but just learning how to apply that for our aquifer in our region. And that's what I wanted to ask. Have you done a lot of work in Southern Africa, in the aquifers in Southern Africa, or is it something that not always gets done from your side?
Yeah, southern and not in terms of really specific to hydrology, but general and agrohydrology where we monitor crop conditions. I have worked on what we call WRSI, Water Requirement Satisfaction Index, whether there is enough rainfall to meet crop needs. So that product is also available on the FuseNet side. So, but I have not worked in really aquifer studies in Southern Africa. But as you said, for example, recharge estimation, these products are readily available to quantify any recharge or withdrawal from if there is any groundwater pumping beyond the recharge limit. Yeah. So these kind of things can be studied through these products, ET. So is there a balance between recharge and withdrawal? I have not specifically worked to answer your question on groundwater hydrology, but yeah, the input data sets for that will allow to study those kind of water resources is available.
Yeah, I mean, I think the also important thing for me is that it doesn't seem like to do this kind of analysis you need to have that sort of on-site water monitoring kind of systems, and it becomes almost like a desktop analysis of a very local area. Is that true? Is that a good impression that I get from the presentation that you've given?
Yeah, I think because as a first cut, especially transboundary, basin stuff, you are better off using a lot of satellite data because the countries around the basin, they may not give you to assemble a good picture what's happening in the entire basin, but satellite gives you a uniformly acquired data over the basin. So I think this would be the first stop, should be satellite observed data. And then you can get in situ data to kind of refine your model. If you're changing storage assumption, is that correct? Well, if there are piezometers data, then that would be very helpful. But you could get a very good picture by understanding water budgets at a basin scale, which are available from remote sensing now.
Yeah.
You can also look at GRACE. We did some work in the Nile Basin where we use the GRACE data. This is another satellite data that just gives you an idea of a change in storage. Like it really combines groundwater. So it's a huge groundwater withdrawal that will show up in this GRACE satellite data, which is really a gravity field. If there's a lot of water is pumped in Southern California or part of India, then that would show up. So there are more data sources than I showed.
Yeah, real quick, Clara, that would underscore what Gabriel just said about the importance of monitoring storage change. That was going to be one of my short epitaphs. That is that storage change really helps you understand the balance between what's being pulled out of an aquifer, so to speak, and what's being recharged into it. So, what Gabriel said about being able to estimate, or at least some idea, starting point of what recharge and withdrawals will be from water use. Those are really key groundwater hydrologic budget terms. So you can have a starting point without having a whole network of wells and a whole network of stream flow gauges and so forth. That's certainly helpful, but I'm just saying this is a way to get a starting point on some of those key hydrologic budget terms.
Yeah, absolutely.
Exactly. Good summary. Yeah.
Thank you. We'll get your presentation, Mark. We will. Don't worry. Because I remember you gave that talk also a little bit when you came to your visit in Southern Africa, and I was very interested in that specific storage change. So we will work towards that and hopefully have it face to face when you come back to the region on your next visit. I don't have any other questions for Gabriel or any other comments on the presentation. So I would like to thank you, Gabriel, very much for having, being very good to us and understood that sometimes things don't happen as we plan, as much as we try, and for having rescheduled this talk with us. We're really appreciative of that. And thank you, Mark, for once again having selected a very good speaker with very important and also sort of adaptable cases for us to use in Southern Africa. So thank you both. Thank you for your time and your availability. And enjoy the rest of your day, and we'll speak again soon. Thank you.
Sure. Thank you so much for the opportunity. It was great. I enjoyed it.
I'm glad.
Thanks, Gabriel. Thanks, Clara.
Thank you.
Thank you.
Thank you very much.
Bye.
Bye.
Bye. Bye-bye.
Bye.
Hello?
Hello?
Yes.
Who is here?
Very good. How are you?